the last lecture we talked about the linear SVM, right? So we are looking for a linear margin. So it's not a linear boundary, but a margin, well, to separate two classes. And the next question we want to discuss is how about we are dealing with a dataset and there is no clear linear margin on this dataset. So, well, I can give you a very small example. Like for this one, we are only considering one feature, and that feature is x, right? Okay, only one feature, and then we have the green samples in the middle, and then we have the blue samples on two sides. So in this case, even though we only have one feature, and this dataset is not linearly separable, because we can't just draw a single line to separate those two classes perfectly. And in this case, how can we deal with the classification? Well, this should be a easy enough classification, but we just can't draw a single line to separate them, right? So, well, one of the trick we can do is, how about we introduce a new feature? And the new feature is we take the x and then we do x squared, and then we take that as a new feature. We call that x2. So we are by adding new squared feature to this feature space, we are introducing more features, and by adding those new features, and guess what? Now this dataset is now linearly separable. So if we just draw a line here, and then we can separate those two classes, right? So this is a trick that people sometimes may do. We are adding new features, new polynomial features, to make the classes easily separable. So we are going to use this tool to moon-shape dataset again. And after that, we are going to create a pipeline. And in this pipeline, we are adding one new piece, and that is polynomial feature transformer. And after that, we still have to standard scalar and then the linear SVC model. Okay, so the first piece is a new part. So, well, and for the polynomial feature transformer, say if we are specifying the degree to be a 2, and we only have two features, a and b, and by adding new features with the polynomial feature transformer, and we will introduce a constant feature, and of course this is usually not that useful, and we will have the a square, a multiplied by b, and b square. Okay, so the highest degree of polynomial is 2 in this case. But look at that. Other than a and b, we also add a square, a multiplied by b, and the b square, right? So degree as 2, we are adding 3 more polynomial features. And how about the degree as 3? So if we're doing the degree as 3, we will add all those degree 2 polynomial features, and plus we will have a cube, b cube, a multiplied by b cube, or a cube multiplied by b. So if we are doing the multinomial features with the degree as 3, and then we are going to add even more features. So think about that. Do we really want to do a polynomial feature with the degree as 10 or 20? Well, that could be really a lot, right? So usually when we are doing the polynomial features, we want to make the degree a reasonably small number. To be honest, I have never seen people add polynomial features with a degree more than 5 or 10. That's just a lot. Okay, and then we can create a pipeline. So in this pipeline, well, the first part of the polynomial features, we create a polynomial features, and then we specify the degree to be 3, and the scalar is a standard scalar, and then we also add a linear SVC model. Okay, so after that, we want to use this function to plot the decision boundary, and you will see this is our decision boundary. So it seems that, well, even though this decision boundary is not perfect, but somehow by adding the new polynomial features with degree as 3, we are able to find a good decision boundary, even though it is a linear decision boundary on the high degree polynomial features. Well, in the 2D plot, you will see that is a curve. But however, in the high degree polynomial features, and that is linearly separable. So the next thing is, well, instead of adding the polynomial features, and in the SVM, we have an even better thing, and that is called Kernel Trick. So, well, it will give you the same or very close result as you can get by adding new polynomial features. But SVM can do this without actually adding those new features. So this means if you're doing the kernel trick, number one, you are going to get roughly the same thing as you can do with this pipeline. However, you don't really have to add that many features, so the running time with SVM might be a little bit faster than this version. However, adding a degree of 10 or 20 polynomial features, that still sounds a lot to me, and your model will be very slow. So be very careful on picking the degree of the polynomial, no matter you are doing the polynomial features or you are doing the kernel trick with the polynomial with the high degree polynomials. Okay, so we want to do another pipeline, and in this case, we are using the SVM model, but not the linear SVM model. We are using the real SVM model, and we are using the kernel trick as the polynomial, and we specify the degree as a 3. Okay, so since we are using the real SVM model with the polynomial kernel, and then we don't have to do the polynomial features anymore. And the next thing we want to talk about is the degree of the polynomials. So we are trying to do a comparison, and on the 3-degree polynomial versus 100-degree polynomial. So 100-degree polynomial, that is really a lot, and usually we don't do that. But we want to do a comparison on what are the differences. Okay, so on the left side, we have the decision boundary of the polynomial degree as 3, and on the right side, we have the decision boundary for the polynomial degree to be 100. So if you see the left side, so on the left side, the first thing I see is there will be some misclassifications, like this green dot, and it will be classified as blue, and for this blue dot, it will be classified as green. But overall speaking, I think the decision boundary on the left side with the degree as 3 kind of makes sense to me. And how about the one on the right side with 100-degree polynomial? And well, I still see some of the misclassifications. Well, but the decision boundary in this case looks weird to me, and this might be a overfitting. Okay, so our model learns too much or too hard from the training set. Well, and the curve looks weird. Even though it is an overfitting model, the performance may not even be as good as the one on the left side. So the point I'm trying to make is, well, be careful with the degree of the polynomials. Unless there's a good reason you don't want to make the polynomial degree that high. Okay, so I will pause the video here, and I will continue in the next video.